And is Andrew here? Yes, Andrew is here. All right, take us away.
Okay. Hi, everyone. I'm Andrew from the AO team. So this app, we're building a QAT workflow or a quantization-aware training that would integrate with the PT 2.0 stack. And last week, we got a ton of feedback from the core edge compiler teams that we ultimately decided on a workflow that would essentially call torch dynamo.export first, get an A10 graph from that, and then pass that to torch compile. So I did an initial experimentation to confirm that this flow works without errors on the toy model, but uh, I'm also aware that people on the core team are looking into a few corner cases where uh, calling makeFX and then passing the result of that to AOT autograd currently fails. And then I think there was a PR that went in recently that adds the pre-autograd equals true flag. But from speaking with Brian, my impression is that this is not stable. Like it's not very well tested because it's relatively new feature. So I think from the AO side, our ask for the core team is what would be the next steps to make this more robust, and also how can we extend these changes to torch dynamo.export, because that's the API we're relying on. Yeah, wondering if you guys have any thoughts on that.
Sorry, so just to check in on the ask. So the question is essentially, basically, you're telling us that the AO team is using export as it exists today to do QAT transformations, and you're wondering if the changes we're making will cause problems for you going forward.
Uh, I guess more like I think the changes you're making will help solve the problems going forward. But then, yeah, just wondering what the next steps of those changes will be.
Okay, is Brian here?
Yeah, I'm here.
Brian, do you want to give us basically a update on the current status of these various features, and then what's on the short term like plan?
Yeah. So I think current state is basically, so one thing you were talking about a second ago was you were saying you run makeFX, you'd get a graph, you do stuff to it, and then you send it to AT Autograd, and you're saying you heard that there might be some problems with that. And like one known thing is that makeFX doesn't preserve some torch APIs in the graph. And so like in some cases it'll work, and then in some cases where you have extra weird stuff in your graph, like torch dot with torch.nograd or something, then those might disappear from the graph. So basically, like it'll work in some cases and won't work in others. Um, I landed a PR last week that was basically add a keyword arg to make effects pre-autograd equals true. That instead of tracing all the way through the dispatcher, it basically stops at the autograd level and produces a graph that's the result of tracing through A10, but before autograd. And so in theory, you can like run makeFX with pre-autograd, get out a pre-autograd graph, do transforms to it, and then send that resulting transform graph through autograd in some way. And it's not being used anywhere right now, so it's not very heavily tested. And there are some cases, it's similar to what I was saying before, there's some cases where it's known to not work. And I think we should fix them. I'm not actively working on that right now, but that's sort of the current state. Alvin, you have a hand raised.
Uh, yes, I'm just wanting to get some clarification because Andrew was saying at the intro that they want to use export, but then you're diving into how to use each of the compile components independently. Like, uh, are you not using plain export basically and using components directly? Can you clarify exactly what you use
Yeah,
here?
so we're using dynamo.export, and then we'll do our own custom pass, and then we'll pass that to torch compile. So those are the only APIs we're touching. We're not calling the internal ones. But based on my understanding, Torch dynamo.export currently calls makeFX internally. So,
Actually, just to clarify, you're calling with A10 ops true. Is that correct?
yeah.
Natalia?
So I talked to Horace briefly about this pre-IoT tracing, and his concern was that it will drop operations that are not A10 ops, such as grad, no grad, or setting CUDA streams, or whatever, things that are Torch ops now. Brian, how are we handling that? So what happens if we cannot make effects through a graph because it's not at the correct level?
Yes, that is exactly right. So in exactly those cases, those ops will be dropped on the graph. And I feel like that's something we want to fix. I'm not actively working on that in the next week or anything, but I agree that that's a problem we should definitely fix.
Okay, so I'm gonna swing. Oh, go ahead.
Sorry, can I ask a loop question, just like practically what this means? So quantization does add some objects in its passes which use no grad. So if I understand correctly, if you are Torch compiled for that, then no grad will just not be respected. Is that correct?
So
if you
go ahead, Brian.
Yeah, go ahead. Oh, I was going to say, if you use makeFX and the thing that you pass to makeFX has a no grad in it, the no grad will disappear in the final graph that you get after makeFX. And that's true for normal makeFX. That's also true today for the pre-autograd makeFX.
Sure. Well, basically, let's assume I'm a user and I have no idea what makeFX is. I have a model which has some no grad calls and I pass it a Torch compile. Is it going to do the right thing, or is it going to like silently break something?
Well, this is a weird question to ask because there's no UI. These are just low-level tools that do certain things, and it's sort of up to, in this case, Andrew to put them together. But let me think. So thinking about your situation end to end, what it sounds like is, Andrew, so first question, you do want the pre-autograd graph. Is that correct?
Right.
And question 2 is, you do need to Torch compile it afterwards and have like gradients work on it, correct?
Yeah, this is for training.
Yeah. So essentially, Andrew does not have all the pieces he needs, especially if the transforms are inserting no grads or things like that. Well, actually, okay. Actually, it might work. So essentially, the way you use Brian's tooling is you would. Okay, so we don't have this right now, but we would add a pre-autograd flag to Torch compile somehow. Sorry, Torch Dynamo export somehow. And then you would run your transforms on it. You would be allowed to insert no grad blocks, and then you would Torch compile the result. So that will work as long as the original program provided by the user doesn't have any non-trivial no grad or enable grad blocks in it.
Right. Yeah, that'd be
essentially your system will work only if the graph that Dynamo export pre-autograd produces faithfully replicates the original. As in, if you just went ahead and immediately Torch compiled that, it would do the same thing as the original. That sounds like enough to unblock. It's not a good long-term situation, but I don't think you probably don't have no grad blocks in the original model.
That's my understanding.
One question, Ed, is on principle, is that something that we expect to work, to literally call export to get a new function and then Torch compile the function you got out of export?
My opinion is yes. This is in the sort of FX ethos, right? We are Python to Python transforms. After you do your transform, you've got Python again. You can recursively run the stack on it again.
So that sounds good. So I think from what I understood from a silly question, then you wouldn't have an issue after you transform because you rerun Torch compile, and Torch compile will handle these no grad blocks.
Exactly.
Cool. Sounds great.
Sherlock?
But you need to run torch compile, not low
Yeah, you have to
level
run torch
AOT
compile,
directly.
not some weird other thing.
So I have a question for makeFX with a pre-autograph flag set to true. So in this case, can we still run decomposition?
So I think the answer is yes. Yeah, you can pass in the decomp table, and the ops that you decompose to should all be like ops that have derivative formulas that we can run autograd on later.
So when you say you set a stop sign at the autograd dispatch key, like what's the implication of the offset it resulting when you set this flag to true? For example, like, are we gonna see the same set of operator if we have the pre-autograd set to false?
Actually, let me refine Sherlock's question for a moment. So when I do pre-autograd tracing, do I do composite implicit autograd decomps or not?
Yeah, that's a good question. I think the current state is that we do not do composite implicit decomps in pre-autograd tracing. I guess I could see arguments either way.
So then to return to Sherlock's question, the answer is you would get more operators than the standard set because the post-autograd operator set will never include composite implicit autograd ops.
So magma will be included in the pre-autograd.
Yes, matmal would be included pre-autograd.
So this is a heads up to Andrew then. You're gonna see a different set of ops. So the original transformation that you wrote for the jury's pass might need a bit of adjustment because the graph is slightly different.
Natalia?
Is it easy to send in the decompositions that are not valid for pre-autograd? Because most of our decompositions are written without any thoughts of producing correct derivatives in mind. So I guess it's not a criticism of the current state, but we need to bring more order to our decomposition assortment, because otherwise it would be easy to use this thing and get wrong derivatives.
This is that thing where we don't have composite compliant decompositions. Like if we're doing pre-autograd and your decompositions also have to work for tensor subclasses, but a lot of our decompositions don't.
Yeah, subclasses is one thing. Things like clamp is another when it's easy to write the composition to produce correct results, but not to produce correct derivatives.
Yeah, I think composite compliance is a different thing because you can have a composite compliant that gives the wrong autograd formula.
Yeah, and I was just pointing out that there is a problem also with composite compliance because if we're doing pre-autograd, because when you start adding tensor subclasses into the mix, then you don't want those to run through those decompositions.
Okay. But we also don't have anyone who's working on like categorizing our decomps. So dangerous decomp table API for makeFX pre-autograd. Only some decomps are okay to do. Any more questions, comments? Andrew, are you satisfied?
Yeah, I don't fully understand all the details you guys just talked about, but on a high level, I think what you just said with like some form of dynamo.export with pre-autograd equals true, if that works, that's exactly what we want.
Okay, so then one more question. So no one is signed up to add pre-autograd to Dynamo export. So Brian, I'm putting you on the hot seat. This is easy, right? We just need to plumb that to the makeFX call that Dynamo export does.
Yeah, I think it just depends what we want to do. But yeah, just like a super vanilla way of getting torch.export to run pre-autograd tracing doesn't seem like too much work.
Okay, do you think you can throw up that like 2-line PR, however many lines it is? I think it's a 2-line.
Yeah,
PR.
I think I can do that. I had one related question just about like the workflow. So you were saying a second ago that like the user UI is first run torch export, then run torch.compile. This is probably like a basic question, but is QAT meant to be like a full graph only thing versus partial graph?
Right. Yeah. Currently, it's a full graph thing.
I see. Okay. Like so in my head, what I'm picturing is if you're using torch.compile and the idea is like we're doing all of this runtime stuff of like we're reusing all of the torch.compile runtime machinery, like how is that different from just running torch.compile full graph equals true and then inserting some way to do some pre-autograd graph passes?
So I guess, yeah, I'm not sure if I fully understand that, but essentially what we need is an A10 graph before we do our own passes. Like our pass before autograd is a prepared pass, so it expects an A10 graph as input, and also the output would contain mostly A10 ops as well, and then we will pass that to Torch compile.
Let me try to give an answer in 3 parts. So the moral answer is there is no difference if you stage it like this versus integrated in. The practical answer is you have no way of actually turning on a pre-autograd make effects in our end-to-end compiler stack. So they'd have to like add that hook point. There's no hook point, so they're not doing it this way. They're doing it with the APIs that actually exist. And the philosophical argument is something like maybe it is okay, like as in it is okay to have a compositional API where you like do it in steps that are visible to the user as opposed to shoving it all into the compiler stack.
I see. I can buy the compositional argument in terms of APIs that don't exist. Like in theory, you could do it the same way that Inductor might do it, right? You specify like my custom backend, which is just a function that like does pre-autograd tracing, then calls AOT autograd, and sort of like all happens under the hood.
Right. Yeah. So I think from talking to Sherlock, we also brainstormed some potential solutions related to like using custom compilers, but I think from the user's perspective, it would be too much code for them to write just to use our APIs.
Okay, well, let's move on to the next topic. All right, Richard, take us away.
Sure, let me share my screen. You guys see the screen?
Yep.
Cool. So I'm going to talk about improving custom operators, in particular for purposes of PT2. So we're just going to walk through this doc. It's a couple of pages long. Feel free to stop me at any time. I'm mostly looking for design feedback on the later sections. So let's start with some motivations. So users want something like torch.fx.wrap, which is an API where you can just shove any random, like any Python function into the FX graph. And there are like 2 main use cases that people have come to us for. So first is people have custom kernels. They have like a custom forward pass or a custom backward pass. Might be written in Python, might be written in Trident, CUDA or C++ or something else. And they want this operation to be in the final FX graph when you torch or compile. Use case number 2 is people are doing things like exporting their program. And when they're exporting their program, sometimes they want composite PyTorch operations to not decompose. One example is like f.linear. They don't want f.linear to decompose into the mess that that A10 matmul decomposes into. Another example is multi-head attention. Some people want to preserve multi-head attention in their graph, so they can do things like lower it to a faster attention kernel. There is some overlap with the pre-autograd work. Like if we did have the pre-autograd tracing working, maybe we wouldn't need these, maybe not, we're not sure yet. In addition to preserving PyTorch operations, people also want to preserve NN modules, which is a bit of a different story. And just one pain point, PyTorch does have a custom operator API in C++. You can access it from Python as well. And these APIs are pretty difficult to use. So we've had like many like existing PyTorch models internally use the C++ custom operator API. And we've encountered problems where things work correctly in eager mode, but not under torch.compile, because these operations are registered correctly for eager mode, but not really correctly to work with torch.compile. And in order to actually figure out what's wrong and debug this, you need a really good understanding of like PyTorch internals, like dispatch keys, auto-write internals, etc. And we've got a lot more use cases collected in this document from a previous discussion. Any questions so far about motivations? Okay, so I'll talk about sort of why this is difficult. Like, why can't we just provide something like torch.fx.wrap that works with torch.compile? And the reason why torch.fx.wrap works is torch.fx is just one subsystem in PyTorch, and torch.fx.wrap literally only works with torch.fx. Compared to torch.fx, torch.compile is super complicated. You've got a really long stack going on. And so for an operation to work with PT2, like it needs a bunch of things. Like we need to know if it's functional or not. Only functional operations exist in the IR at the end of the day. It needs a shape propagation rule, so it works with dynamic shapes in PT2. If you're doing training with this operation, then it needs an auto-grad formula. So Torch, the PT2 stack is pretty complicated. A simple API like torch.fx wrap will not solve all the problems, because we need to figure out all of these items. Another reason why it's sort of difficult to resolve the above problems is that a lot of people already have custom operators written in C++, and we can't just update the default behavior of those custom operators to like do something else, because that would be very BC breaking. And so I want to move on to talking about sort of like the goals and what we're trying to solve. Any questions before then? All right. So we've got a couple of goals. The first is sort of just improve safety by adding checks for incorrectly defined custom operators. There's a couple of ways we can do this. It's not really specified in a goal like how. Like we can add more safety checks to that trigger at runtime to existing custom operators, or we can provide an easier way for people to sort of test things on their own if their custom operator is correct or not in general and in the context of PT2. We want people to actually be able to register custom operators without feeling a lot of pain. So we want to add a simple custom operator API that does not require people to be an expert with PyTorch internals. Aside from these P1s, we've got some P2s. We want to add a convenience API so that people can sort of convert their modules into custom operators so that they don't have to manually refactor their code to use custom operators. And another P2 is, yes, we can kind of generate like things like autograd formulas and so on and so forth if you give us a for certain custom operators, but I'm not sure if this is a good idea. Cool. So we're going to talk mostly. Yeah. Question.
Yeah. So on the second point, then what does it mean to say that the API should let people optionally specify these different kinds of behaviors?
Yeah. So the way to think about any custom operator API is that like you've got a custom operator, and then PyTorch has several high-level subsystems, such as like autograd, shape propagation, and functionalization. And the custom operator API should let you specify the interaction between the operator and these subsystems. So that's generally what we mean by specifying behavior.
Right. So what is optional about this? Like let's say somebody does not specify what happens with regards to the interaction with the shape propagation.
Yeah. If you do not specify like a shape propagation rule, we should clearly raise an error telling the user, hey, you have not specified this. We do not actually do that today in some cases. Today, sometimes the error
So
is
we
very
would
opaque.
just prompt them to add those behaviors.
Yes, we would prompt them to add these behaviors instead of the user seeing an error with fake tensor and not knowing why they have a fake tensor.
Okay, but yeah, otherwise I was having some trouble reconciling that with the last one, which was
Yeah. Some other things that are optional is like the odd grad formula is actually optional. Depends on if you're doing if you're doing training or not. If you're not doing training, doesn't matter. If you're doing training, we should yell at you that you don't have an odd grad formula. Kamesh?
Yeah, so I was gonna ask, like, so for the P2 that you said, like, in a convenience to convert an module to custom operator, like one case I can think of is like, how this I've been discussing also with a few folks like Sherlock, also like how linear decomposes into different ops. Does it also apply to things like that? Like I can understand and linear, fine, but what about f functional dot linear?
So epsilon functional linear should be covered by like this P1.
I see. Okay.
In the sense that so one naive API is the user can register their own linear custom operator that has all of these things, and then they're good. But we can also make it a bit easier for them.
Right.
More questions?
Is the complexity of the PyOp API just the fact that you have to know about keys? If there was like some boilerplate around default PyOp creation, would that make that P1 simpler?
Which P1?
Add a simple custom
Yes.
operator API.
Yeah, so the thing behind this P1 is that we're just going to not tell people about dispatch keys or torch library. So like one example is AutoGrad has a bunch of different dispatch keys, and you need to know what the AD in place and view dispatch key is. We're just gonna hide all of that behind just the user giving us an AutoGrad formula, and we'll figure out the boilerplate for all of those dispatch keys by ourselves. Okay, so I'll mostly go into talking about details about the first two goals. When I'm done talking about the first one, we're going to go into a proposed API design for the second goal. So the first goal is PyTorch is actually very good at testing like our own PyTorch operators. We've got tests that like metatensors work, that our operators are traceable, that under AOT AutoGrad, the operator like has the same AutoGrad semantics. So we want to make it easier for custom operator authors to sort of know that they're implementing their operators correctly by giving them a way to actually use these tests. One way to do this is to offer something like a grad check like API, where the user can just give us a function and sample inputs, and then we just run these tests for them. So yeah, that's all I have for custom operator safety. I will move on to the second section. Okay, so this document, most of this document is about us proposing a new simple custom operator API. In particular, some things up front. User needs to provide us a schema. The user does not need to understand PyTorch internals, which is what we were talking about earlier. They should not need to know what dispatch keys are. The API is Python based. It's kind of hard to write a better API than C++ without using CodeGen. And we want the API to be safer than using the raw like Torch library API. Yes, Vaz?
Would you rewrite all the existing PyOperators in this?
By PyOperator, do you mean the higher order operators or
Yes.
something? Is that yes?
Yes.
Yeah, so the higher order operators are different from PyTorch 18 operators because they don't require schema. We would not rewrite the higher order operators. They're in their own separate class.
Okay.
Cool. So I'm going to start to go through the API. So in this API, you can define a custom operator. And there's sort of like 3 entry points into defining a custom operator. First one is like, let's say you have an operator that calls some custom C++ CUDA, etc. code. and you define a custom operator, and you add implementations for it. So this is where like you can use foo.defimple to say what its implementation is for these two devices, foo.defmeta to add a meta registration, which is your shape propagation rule. Entry point number 2 is if the user can promise us that they have an operator that only uses regular PyTorch operations, like it does not call into like, I don't know, NumPy or C++ or CUDA or Trident, like manually, then we can actually generate the implementation and the meta rule for the user. So all the user needs to do is just add one single decorator with the schema, and then we have generated an operator for them. Yes, Ed?
Minor bike shed.
Yep.
Will you support like decorating foo.impl and foo.meta in entry point 1?
I do not want to support that because I want to add new arguments in the future. But you can.
But
these
you
already
can,
support
you can still
decoration.
do that, right? So it would be at foo.defimple, and then all the extra arguments you want to add can be added that way.
Like this?
Yeah, like this.
Sure, we could. Should we?
My vote is yes.
Okay. We can definitely do decorators.
Torch compile already works like that. You can either pass the function in explicitly or use it as a decorator.
And if you have a decorator, then you can always not use the decorator if you don't want to, right? If you're doing some kind of scripting or whatever.
Yeah, but it looks a bit weird to not use a decorator, but it's okay. Weird as in you have 2 calls.
The way Torch compile does it is you just take the argument you get in the first function. If you don't get a function, you expect to be called with it.
I see. That seems too magical. But maybe it's okay.
Yeah, it's Pythonic, so yeah.
Sure. Sorry. Okay. Any more comments on that? Cool. Moving on. The third entry point is you might already have an operator defined in C++ or maybe even in Python. And you should just be able to create a custom op like from that existing operator. And so those are like the 3 entry points to the custom operator API. All of these produce a new object of class custom op right now. It doesn't have to be this. It could just be like the existing op.overload, the existing torch.op.overload packet. Will.
Yeah, for entry point 3, what's the assumption? Is there an assumption that the operator in my new lib is like just a C++ function, or is it any other assumption that it's somehow registered to Torch in some way?
So here, there has to be an operator named this somewhere in PyTorch's operator registration library. It could have been registered via C++. It could have been registered via Python using the raw Torch library API or in some other way.
I see. So wait, if you did, I'm a little confused about what you get from using the new API, apart from it being a nicer way to register things. Like, is there going to be some functionality that you get access to by using this third entry point?
Yeah, so you get a nice way to define an autograd formula using this API that I'll demonstrate later. But if you're using the raw like C++ operator registration API, it's kind of difficult to register autograd formula, right? Because you create an autograd function in C++, you need to know which keys to register it to, like most of the autograd keys. Then you need to make sure your like AD in place and view key is correct.
I see.
So just as an example right here, like you could just define the backward formula like right here in one line.
I see. So this is a case where we had a custom op that was only forward, and now we can do the backward more easily without having to change the custom op a lot. Okay.
Yep. Without having to write the backward entirely in C++.
Yeah, no.
Okay.
Okay.
Yeah, I was just going to ask this. You can define autograd based on the existing custom C++ operator also for meta kernels as well, right? All the other stuff.
Yes. using the existing C++ operator registration API, you can define all of these things already. This simple custom operator API just provides a nicer way to do so. That has fewer flip buttons. Ed?
Yeah, I've got another bike sheddy thing.
Yep.
How come you want two different functions, one for existing, one for not? Like if I define something and it happens to match something that we've already got something for, like that seems fine. I should just switch to the existing universe.
Can I answer that one?
Yeah, go for it. I will keep thinking.
We have dangling impulse ads, so it's hard to know if something will be defined in the future or not by someone else.
Okay, then I have the reverse question, which is when you implement custom op from existing op, like what do you do if you haven't loaded the library yet?
My expectation is you have dangling impulse are fine, so you will register a bunch of dangling impulse that will end up all good and well once the C++ code does define it.
No, but like, so realistically, the only thing that's going to happen here is like I'm trying to override something from Torch Vision, and I haven't imported Torch Vision yet. Like it feels like to me like that's just error. Like the dangling impulse situation, I agree can happen, but in reality, once you're in Python and not in C++ static initializer land, you basically can assume that all the defs have shown up.
Sure. If we can assume all of defs have shown up, then we don't need this entry point. I agree.
Well, I mean, so here is one pitch for this entry point, right? So in your formulation here, the user still had to specify their entire schema string, right?
Yep.
If you're doing the existing op, you don't actually need to put in the schema, right?
Sure. You just need like the name of the op.
Exactly. Okay. Bike shed over. We can talk about this more later.
Sure. All right. So those are the three main entry points. Going to move on to talking about how defining rules are necessary. Sorry, how people are going to define rules that are necessary. Yanon.
Is overload going to be supported? Let's see, if I want out variant of a custom ops, will it be supported?
Thinking right now is no, but if you want it, we can talk.
Okay.
Overloads are just very hard to deal with in this situation, like with custom ops.
Bad news is probably needed. We can talk offline.
By the way, I think out variants are a thing in our codegen world because we need them to be very specific, but it might be that you only define the out version of the operation and you don't need overloads because you only need that implementation.
Are you saying you suggest all custom ops be out variants? Then we can derive other forms of operators? Derive other variants of the same operator?
The ones for which you want an out variant, yes.
Chiming in for a moment, my preference here is for this machinery to automatically generate out variants. Like my heuristic in my head is if CodeGen does it, then this API should do it too.
Sorry, so for CodeGen to actually generate the out variants, we need to specify here's an op, here's the out variant in native functions.yaml. So the user will need to do that as well, and then say how to stitch them together. Unless the user just gives us an out variant.
I'm going to ask for pony. So my pony is you just do the schema, and then we'll just tack a dot out overload on it and put the out argument in the normal spot. And like maybe you can have a knob for customizing it if you need, but yeah, like
there are actually some nuances in generating this out variant schema. I think there are some operators that take in like essentially tensor options as arguments, and then out variants, those are gone. And that's allowed. That was even encouraged. That couldn't easily be generated automatically.
Do you have an example of an operator that takes in tensor options that needs an out variant?
Yeah, I can give you one later.
Okay.
So here's another
I think the factory functions.
pony request. I think this API should eventually be able to handle tensor options in a reasonable way. Not V1, sure. But like, you know, yeah. Like I think it's a common enough pattern that like it's worth special casing for.
At the risk of tacking on even more things, like you could also imagine defining just an out equals variant in Python, or just an in place variant, and having like all the variants be automatically generated based off of it. And like the C++ code gen does some version of this, and there's like some mumbling because like I don't know, like I can imagine what, like if we require the user to never define two variants and we like explicitly say they have to define just one, then like we could define all of them. But also, yeah, definitely not immediately needed or anything.
So this is just go on.
Yeah, another point I wanted to make was at some point we need to think about backward compatibility of the operators themselves. And one common way of doing that is to add more options like with defaults and so on. So the more we auto-generate these out variants, the better it will be for that compatibility story, because the less the user will explicitly have to specify.
That makes sense to me. Alvin?
Yeah, I just wanted to mention that I think all of these examples are just general examples of things we could automatically generate, from functional to out of place to out equal variant. There is a whole collection of them depending on which feature you're looking at. And I think all of them are feasible. I don't think you should record them for V1, but I think all of them should be doable. Basically, anyone that has one such feature and they say, I want all the custom ops to support that in the future, then I think we would accept doing that.
Sure. All right, let's get down to go to the real section. Sorry, did someone say something?
Sorry, we essentially have like out generation wrapping with all of our like decomposition work. Like, I don't know, seems like something that could potentially be reused.
And yeah, we already have these cogen, these things in the cogen as well. So definitely a lot of reuse that can happen.
Yeah, so there are a lot of things from this API that we can reuse from the code gen, and we probably will end up reusing. More comments? Okay, so as we mentioned a while ago, in order for an operator to work with PT2, user needs to provide us 3 things. They need to provide us a shape propagation rule so it can work with dynamic shapes. They need to provide us an on-grad formula if they're doing training. And they need to provide us a functionalization rule if their op isn't functional. So we'll go through like how these look like one by one. For shape propagation, user can just give us a meta formula. The meta formula is just a bunch of hydrochops. Now, one thing that people have asked us for is how to write a meta formula for something that's data dependent. And from talking with Ed, like the current thinking is we give the user some way to grab a shape environment so they can construct their own unbacked symbols to return as the meta formula for data dependent operations. Ed.
Actually, I changed my mind.
Okay, mine has been changed.
I'm going to tie it to fake. Like, we should have some way of registering a fake tensor implementation. It's the main reasoning here is that fake tensors are scoped and meta tensors are not. And for the like shape stuff, you need a scope. So fake tensor is more logical. And on Tuesday, I did propose what if we only had one fake tensor environment, but no one liked it. So I'm giving up on that idea.
Okay, so we need to change this API a bit so that.
Yeah, so this would look different, I think.
Yep. Cool. Moving on.
Would you is there expose like setting up like a value range in the output in the first API? You know, we're doing that with our own registrations.
I would not block. We're going to solve the define fake tensor thing for data dependent separately. So it's orthogonal to Richard's project.
Sorry, will a user need to be able to define value ranges for their unbacked symbols?
Generally, yes. But
Okay.
we usually just ask them to constrain range it manually. Like that's what they look like right now.
Oh, sorry, using the constraint API.
Yeah. There's some other problems though, like how we're going to handle caching and memoization and stuff like that. But yeah, I don't think this room needs to help with that design problem.
Sure. Any more comments on shape propagation? Okay. So autored formula, I don't remember what foo was. I think foo just called sign. Okay, assume that foo just calls torch.sign. The way we generate autored formula, we're targeting currently an API that looks a bit like how the root.jam looks like. So you can pass in a lambda, if I pass in a dictionary for each input, you say sort of what the formula is. So for foo, we can call foo backwards on it. Foo backwards can be another operator, or it can be a sequence of operations that are differentiable by PyTorch. So one thing you'll notice is that this function ends up passing the grad's inputs and outputs to foo backward, which means that all of these need to be saved for backward. If you don't want to save them for backward for efficiency reasons, like you might only want to save one input or input.shape instead of the entire input, you have two options. Like one is rely on PT2 to sort of fix your memory for you, or you can provide a safe filter function that actually just filters out what you want to save. That's sort of what we're doing for the auto section. New York.
This is just a question. For sequence of PyTorch understood operators, is that like someone wants to provide a custom op for the forward, but want to use some sort of composite thing for the backward? And if so, why wouldn't they? Like, is this handling the case where they have like a fancy, cool, optimized op for the forward, but not the backward? Like, why wouldn't they just do a composite thing of PyTorch operators only for the forward and have the backward be generated?
So sometimes people have a custom creator kernel for just the forward, but not the backwards, because they don't want, either one, they don't care enough, or two, they just don't have time to write a nice fast kernel for the backward. So yeah, this is a case where people like have custom kernel for the forward, but maybe not the backward.
Okay, cool. Thanks.
Smart show.
Hey, just some quick. I think if people can, I'm not sure. It's just an idea just come out of my mind. I think if there's no custom backward sometimes, would it be make sense for like things like PD2 offer a way to register decomposition, and if the decomposition is just a simple set of ATON ops, right? Shape propagation, autograd, functionalization, it just automatically work instead of letting the user define shape propagation rules, autograd rules, and functionalization rules. Does it make sense to
yeah,
do
so
that?
you're suggesting that the user register decompositions and we just generate all the rules from that.
Yeah.
We can do this. That's the P2, somewhat in the P2 over here. Automatically generate stuff. There are some weird things that can happen. For example, if you want to generate an autograd formula for like using your decomposition, your operator might not return the right things as intermediates that are necessary for backward, right? You might have a decomposition, some of the intermediates in decomposition need to be saved for backward, but your operator needs to actually return those intermediates to be saved.
I see. So basically, autograd itself cannot correctly be generated just from a decomposition.
It can be, but we need to figure out the UX for it. Like we need to tell the user to change their operator so that it returns more things, like some of the intermediates, in order for us to actually really generate for them. But yeah, in the future, this is something we can definitely do.
Yeah, thank you.
Sherlock?
Yeah, in the same line of question, like, do you expect the intermediate activation to be part of the schema?
Yes.
It need to be saved for output.
Yes. The only things that the people can save for backward are inputs, outputs, or just inputs or outputs. So anything that is intermediate activation that you need saved must be returned as an output of the operator. And this is how it works for regular PyTorch operators as well.
But like, what if the schema is different for inference only forward and for inference that need to support?
Yeah, you need two different operators then. So yeah, so if you have a dropout, right?
Yeah.
Dropout takes in a tensor, returns you another tensor. Then this might be fine for inference, but for training, you need a dropout.
You need a mask.
That gives you a mask. And this is what happens. Probably what we don't just have this in PyTorch right now. Like we have something like this, second one.
And I don't think the schema is a problem here, to be honest. You could return an empty mask. You could just, you could detect if you're computing gradients or not. And if you're not, return an undefined tensor for the mask.
Sure. The schema isn't really the problem. The problem is the user gave us a schema at the beginning when they constructed a custom operator. And now we need to modify it if we were to generate an autograd formula for them.
What do you mean?
So the user, when they were registering their custom dropout, they would give us this schema. Tensor X returns a tensor. Another user is like, can you generate an autograd formula for this? And we're like, okay, in order to generate a formula for this, we actually need you to return a new tensor. So we need to change the schema that you have provided us.
But that is an optimization.
What do you mean by optimization?
Can you just regenerate the mask?
Sure. Yes, if we're not doing dropout. Sure.
Yes, and again, right, it's if you are going for perf and stuff, you will have to write your formulas and do these optimizations.
We can regenerate the mask. So Alvin is saying in your backward pass, just regenerate the mask and then just use it. Like rerun your forward and then use it to compute your backward. My question is, who is actually going to sort of do the CSC between the forward and backward pass? Like you probably get the stuff post AOT autograd. So like you have a separate forward and a separate backward graph. So who's actually doing the CSC? And my short answer is no one has actually come to us asking for this yet. So I'm just going to punt this down the line.
What does CSE stand for?
Common sub-expression elimination.
Oh, okay.
So we've got the forward pass it calls the forward, backward pass is going to call the forward and the backward. And now we want to not do the forward twice.
Sure.
But maybe checkpointing will tell you prefer to recompute instead of saving.
Sure.
as one more data point on the dropout, like the low memory dropout, I know for flash attention, they checkpoint some global state to be able to recompute the attention mask, like and they save it in the context for backward for like a custom autogrid function. So that wouldn't play nice, I think, in this, but there's ways around it.
No, I think this is exactly what I was saying. In this case, they don't want to save the mask. They prefer to recompute it during the backward.
Okay, so that's AutoGrad. Quick DR on functionalization is the schema is functional. Sorry, go on, Elias.
Yeah, related to AutoGrad, like I know previously we had some discussions about how to support set RNG state, etc. And I think there was like two proposed solutions. One was like to annotate metadata about what the like the offset was for the RNG and then like the initial seed. And then I think there was also some discussion around like potentially like just having those as explicit arguments to our RNG ops. I don't know if that got resolved, but if it didn't get resolved, like it would potentially have an interaction with custom RNG ops here.
Alvin, do you want to take this one?
Sure. Yes, I think we are going down the path of using explicit arguments and a functionalization like path to translate from the stateful to the stateless version. And the way I see this being linked is that, yes, these new operators, we definitely don't need them to be native functions. So we can definitely use something like that to very easily create these operators we need.
So like, I mean, then the custom like RNG full user defined operators would need to use explicit arguments. Is that right?
Yes, but we have an automatic way to translate from one to the other during AOT dispatch. And I guess maybe your point is similar to the how we have a functionalization to go from view to out of place. Maybe we will need also something to be able to register or add more RNG to, well, stateful to stateless RNG functions. Yes. But I don't expect too many people write RNG functions.
Cool. I'm not going to go through the rest of the doc, but can I field any last minute questions? Okay, well, we're at time. That's all for me. Back to you, Ed.
No, that's it. See you all next week.